everyone. Today I'm going to be talking to you about our new unit, which is thermochemistry. And in order to talk about thermochemistry, hopefully you realize we have to talk about heat, right? Because thermochemistry is the chemistry of heat. In order to talk about heat, we need to talk about energy, because heat is a type of energy, okay? So we're going to just briefly go over what energy is and the difference between heat and temperature, because both of them are going to be relevant to thermochemistry. So energy, when we talk about energy, it's the ability to do work or produce heat. Now in physics, you'll see a lot of the aspect of energy that's doing work, or work that's being done to either produce or absorb energy. Whereas chemistry, we're talking more about the ability of substances to produce heat. So when we're actually looking at energy in chemistry, we've seen one kind of energy already, especially with our gas laws, and that was kinetic energy. Now remember, kinetic energy is the energy of motion, and we talked about this in terms of temperature. So the faster particles move, the higher their temperature goes. They have more kinetic energy, they're moving faster, temperature goes up. The slower those particles are moving, they have less kinetic energy, and their temperature is lower. Now the second type of energy that we see in chemistry is potential energy. And in chemistry, we often talk specifically about chemical potential energy. So potential energy is energy that a substance has due to its composition or its position. When we're talking about the position of an object, think of like a bike at the top of a hill, right? So that bike has the potential to start moving down the hill and gaining kinetic energy. At the top of that hill, due to its position, it has potential energy. Chemical potential energy refers more to energy that's stored in chemical bonds. So when bonds are broken, oftentimes energy is released or absorbed, and that's that chemical potential energy that we are talking about. Now, we know what energy is. It's the ability to do work, or, as we're concerned with, produce heat. So what is heat, and how does that relate to temperature? Heat is a type of energy, okay? This is energy that's transferring from one object to another due to a temperature difference. If they're at the same temperature, then there's no energy transfer, okay? But when we're talking about energy or temperature differences, think of like on a cold winter day when it's freezing outside and it's really warm inside, you have the heat going. If you open a window, you're not going to have cold air coming in. What you have is the hot air from inside moving out, because heat energy always goes from high to low temperature. From high to low temperature. You are feeling cold when that window is open because the heat is leaving. It's not because cold air is coming in. Cold air is not coming in. That heat is leaving, and that's why you feel cold. Now, when we're talking about heat, we're going to be doing some calculations. So when we talk about heat, we're going to use the symbol Q. We measure heat using a calorimeter. Now, you know that we measure temperature using a thermometer. We can just stick the thermometer in the water or whatever the substance is and get the temperature. We don't have a tool that allows us to directly measure heat that way. We actually use a calorimeter, and then we have to use this equation, which we're going to be using today. Q equals M times Cp times delta T. And this is heat is equal to mass times specific heat times a change in temperature. Don't worry about that too much. You're going to see that on the third board. Or second board. The unit that we use to measure heat is not degrees Celsius, it's not Fahrenheit, it's not Kelvin. It is joules, okay? This is a type of energy. We measure energy in joules or kilojoules, and those are abbreviated J, capital J, or lowercase k, capital J. Prior to now, heat was often measured in calories or kilocalories, and you'll actually see that on the back of nutrition labels right now. The calories that you're seeing are actually a measure of heat energy, okay? But in chemistry, when we're doing our calculations, we're going to be using joules and kilojoules. Now, how is heat different from temperature? We already know that temperature is a measure of the average kinetic energy. We've said that a few times with the gas laws. The faster the particles move, the more kinetic energy they have, the higher the temperature. We measure, or we symbolize temperature with a capital T, and we measure it using a thermometer. The SI unit is degrees Celsius, all right? So that's how we're measuring temperature using the thermometer is degrees Celsius. We can convert it to Kelvin, but the SI unit is degrees Celsius. Note here that whereas the gas laws, remember we always had to use Kelvin as our temperature, we are always going to use Celsius in our thermochemistry unit. The reason is because we didn't want negative numbers, right, with our gas laws, because we can't have a negative pressure, we can't have a negative volume. That's why we're using Kelvin. Here, that negative temperature actually tells us a lot about what's going on in a system. So we want to make sure that we know we want to make sure we're using Celsius so that we can have negative or positive temperatures. You'll see why. Now, thermochemistry, the whole idea of this unit is the study of heat changes that occur. Okay, so in physical or chemical processes, when we're talking about physical, it's like state changes, dissolving. Chemical processes are more of the burning or combustion. But this is a study of heat changes that occur during these. Okay? Now, we're getting a little more specific. We're going to talk about specific heat capacity because this is how we measure heat, right? This is that formula that I showed you on the last board. We use this formula to either calculate heat or we can actually calculate the specific heat capacity of a substance or the temperature or the mass. What specific heat capacity refers to is the amount of heat required to raise a temperature of 1 gram of a substance by 1 degree Celsius. Okay, so think about that pool example. When we're outside and we're stepping on the concrete is really hot around a pool oftentimes, especially in the middle of the summer. That concrete's really hot. However, the water in the pool is not as hot. Why? The reason is the water has a higher specific heat capacity than the concrete. That is a very high, relatively high specific heat capacity. So it takes a lot more heat to raise the temperature of 1 gram of that water by 1 degree Celsius. The concrete takes less heat to raise 1 gram of the concrete by 1 degree Celsius. Okay, so that's what we're looking at. How much heat does it take to raise 1 gram of a substance, just 1 degree Celsius? The formula we'll be using is this Q equals M times Cp, this is specific heat, times delta T. Okay, now Q is heat, measured in joules. Our mass is measured in grams. Cp is the specific heat capacity. Now this is measured in joules over grams times degrees C, right? Why is it all of that? Because this is joules, this is grams, this is degrees C. Okay, so specific heat capacity encompasses all of those. Kind of like our R value, our gas law constant that you saw with the gas laws. Long unit. Delta T is not just the temperature. That delta sign refers to the change in temperature. We figure this out always by subtracting T final minus T initial. It's never the other way around. T final minus T initial. That's the change. We might also abbreviate that TF minus TI, and it's measured in degrees Celsius. Now, the specific heat that you're going to see is water. And water's specific heat capacity is always 4.184 joules over grams degrees C. Always. Every substance has its own specific heat capacity. It's similar to density, right? We can identify a substance based on its density. We can also identify a substance based on specific heat capacity. This is a physical property of substances, okay? Now, the last thing that I have here is when we're looking at our heat, heat is always either absorbed or released. Now, this is why the temperature has to be in degrees C and we want to see the negative or positive there. Because if we end up with a positive Q, that means that heat is absorbed. If we have a negative Q, that means that heat is released. So there is a distinction there, and it's an important one for what we're working with, because whether 2,000 joules of energy is released or absorbed is a huge difference, okay? Now, we're going to look at some calculations. I have two examples. The first one's a little bit more basic, all right? They're not the same, they're a little different. Number one, if the temperature of 34.4 grams of water increases from 25 degrees C to 78.8 degrees C, how much heat has been absorbed or released by the water? Okay? How much heat? That's what we're looking for. That means we're looking for Q. We don't know what Q is. Our mass, I've identified there, is 34.4 grams. Our specific heat of water, remember I just showed you on the last slide, I don't think it pops up right there, the last board, is 4.184 joules over grams degrees C. That's always the specific heat of water. And our change in temperature is TF minus TI, okay? So we're going from 25 degrees C to 78.8. That means our final is 78.8. Our initial is 25.0 degrees C. All right? So when we're looking at this, we have to subtract 78.8 minus 25, and we get 53.8 degrees C. That's our change in temperature, okay? Now we can plug it into our equation. Q equals M times Cp times delta T. I kind of like to call this Q equals MCAT. It's easy for me to remember that way, right? So we're looking for Q. Our M is 34.4 grams. C is 4.184 joules over grams degrees C. Our change in temperature, our delta T, we figured out is 53.8 degrees C. Okay? Grams here cancels out, top and bottom. Celsius crosses out, and we're left with joules as our unit. All right, so Q is equal to 7743 joules. But according to sig figs, 3, 4, 3, we can only have 3 sig figs. 7740 joules. That's one type of example. The next one's going to be a slightly more difficult example. Not bad, not bad. To what temperature will an 85-gram sample of lead, here's our mass, decrease if it releases, this is important, releases 2,080 joules of heat, and the initial, so this is heat, Q, and the initial temperature of the lead, I messed this up, sorry. The initial temperature of the lead is 193.0 degrees C. Okay, so we have the initial temperature. Specific heat of lead is 0.129 joules over grams degrees C. All right, so what do we have here? Q, we know the heat. We are releasing 2080 joules. Remember, if heat is released, that Q is a negative number. So this is negative 2080 joules. That negative is very important. Our mass there is 85 grams. The specific heat of lead is 0.129 joules over grams degrees C. And our delta T, we don't know. Okay, so we're going to solve for delta T first. Then we'll do the TF minus TI. Okay, so Q equals MCAT. And I'm going to rearrange this to solve for delta T. So divide by MC on both sides. And you get delta T is equal to Q over MC. Let's plug this in. We know Q is negative 2080 joules. Mass is 85 grams, 85.0. And our C, our specific heat, is 0.129 joules over grams degrees C. Our units cross off. Joules is gone, grams is gone, and we're left with degrees C. Okay? Now the value that we get here for delta T, and I'm not going to round this yet because we're not done with the problem, is negative 189.69 degrees C. That negative is important. We know that delta T is equal to TF minus TI. Okay? So our delta T is equal to TF minus TI. So I have 189 negative 0.69 degrees C is equal to, we don't know TF, minus TI, 193.0 degrees C. So when you add 193 to both sides, you're getting TF by itself, and TF is equal to 3.3 degrees C. Okay? This negative makes a big difference in what you get here.